I'm going to talk about traditional numerical methods, the bread and butter of HPC until AI came along. And while we do have AI applications, I'm not exactly going to focus on those today. I'm going to try and basically unpack what exactly I mean by a high-order entropy stable method. I'm sure most of you are familiar with computational fluid dynamics in some form or another. I'm going to try and explain why I find these methods so interesting and how I hope that they will end up transforming, at least in some small way, the field of computational fluid dynamics. So let me talk to you a little bit about what my goals are. I am broadly interested in making pretty pictures that look like this. So this is a trifoil in an aerospace or an aerodynamics application. Imagine this as just being a cross-section of a wing on an airplane, and you probably want to figure out if you're flying or if you're landing, then you want to figure out what the flow looks like over this. And you generate some nice plots, and you get this very pretty picture over here. I basically want to figure out the most efficient way, the most efficient and accessible and scalable way to implement these in a robust fashion with strong theoretical foundations. So for the reasons of accuracy and to deal with these complex looking geometries, I basically am going to use some class of high order finite element methods. And if you're not familiar with them, just think of them as numerical methods for simulating solutions to partial differential equations that can use something like this triangular mesh here. So we'll mesh this complex looking object like so, and over each element we'll try and approximate what this solution looks like and then generate this beautiful looking flow field. So these are largely vorticular type features. They tend to be very pretty looking, they tend to be nice. I want to be able to capture vorticular flows, acoustic waves. These are really useful in something like aerodynamics and noise suppression. But I'm also interested in dealing with something like turbulence and shocks. And at least for numerical methods, if you're familiar with them, then you know that these tend to be highly under-resolved in most cases, and they cause a lot of numerical issues. I'm just going to glaze over just the initial theory on why exactly they cause issues, but they're going to show up later. So this is aerodynamics, but you can imagine this being applicable to an engine rotor, to a wind turbine, if you use the magnetohydrodynamics equations to a tokamak. So I would argue this does have energy applications, but I'm going to focus primarily on the numerics. So I am interested in high-order methods. And if you're familiar with them, then this basically is just referring to the order of accuracy in something like a Taylor series that your error obeys. So if I have a first order method, then my error is basically just proportional to my grid size. If I have a second order method, my error is proportional to my grid size squared. And then fourth order, so on and so on. You get these larger and larger exponents in terms of the correlation between your error and your grid size. So if I try and just simulate the simplest possible CFD model problem, this is just moving a Gaussian around and around in a circle. This is just a simple one-way wave equation. And if I use a first order method, if I move this bell around enough, then you can see my numerical solution dissipates everything away to almost nothing. I get very low resolution. And bumping up to second order significantly improves the resolution. Bumping up to fourth order gets me even better. And if I go to eighth order, it looks nearly indistinguishable between my numerical solution and my exact solution. And you might notice that I am actually decreasing the number of elements, decreasing the number of grid points that I have as I increase the order of approximation. So the point in this is to argue that the higher order you are, the more accurately you actually capture these time-dependent dynamics. And this is something completely different than the standard spatial order of accuracy that you might try to expect from a high-order method. So we are arguing that high-order methods are generally a fairly efficient use of your computing power. And this is, of course, a really simple model problem, but it's not that hard to extrapolate to a much more complex problem, and you see some real benefits. This is a standard second order numerical method for something called the Taylor-Green vortex, basically turbulence in a box. And you can see in this example, there's a ton of numerical artifacts that appear in this visualization of something called the Q criterion for identifying vortices. If I bump up to fourth order, it gets much better just by this 2-order increase. And if I go to a whopping 16th order, where I'm decreasing the mesh resolution or the grid resolution at every single order increase, then I get this nearly perfect resolution over here. So a little bit of history. High-order methods have been around for ages, since I think before I was born. That's before the 80s. They have been promising an improvement in numerical methods, a revolution, for almost the same amount of time. Why exactly are they not used? Well, I like to think about this as being one key aspect that our previous speaker talked a lot about, robustness and reliability. So even though you can get incredibly accurate and nice looking solutions, you can also get this. This is the simplest possible nonlinear conservation law, a sort of prototype for fluid dynamics. And what happens is if I evolve this a little bit, then I end up with a shock, a discontinuity in my solution that appears in finite time. So if I run this with a higher order method and the shock gets in the middle of a grid cell, then you see some oscillations that appear. And these oscillations kind of hover around. I can evolve my solution a little bit longer, but eventually they blow up. They crash the solution, my simulation is worthless, and I've burned a couple of 100 compute hours. So this is not great. It, of course, is something that people have been treating, but I would argue they've been doing it using relatively ad hoc methods, adding basically artificial dissipation of some sort to basically say, if I see a wiggle, I'm going to try and damp it out using something like a physical mechanism. And this works okay, but it does have a few issues when you try to really deploy this at scale with someone who might not be familiar with this code. So this is a book that my postdoc advisor wrote, and I really like this quote here. He says, for these complex nonlinear problems where you might see these stability issues, then you should filter. You should add some dissipation. You should remove these nasty high mode wiggles. But you should do so as little as possible, but as much as is needed. And this is in general a good proverb, but it doesn't quite give you a nice formula for how much to do. And what we found in practice is that when you're trying to do this, you end up walking a very, very thin tightrope that changes depending on the problem that you're working on. If I try to simulate one problem with a little bit more turbulence, then I might need to tune my stabilization parameters a little bit differently than if I have another problem where it's mostly acoustic noise driven. So I'm always trying to balance robustness and accuracy if I do it this way, if I basically try and use this heuristic approach, and that is what has led me to these entropy stable methods. So I'd like to argue that these are gaining popularity and they're becoming more of interest beyond the academic circle because they exactly address this issue of robustness and reliability. Basically, in a nutshell, they improve robustness, but they don't do so by adding numerical dissipation. Why do I care? Well, this numerical dissipation is essentially an extra physical term that I'm adding to just suppress things and make sure that my simulation doesn't blow up. But that tends to decrease accuracy. It's not really consistent with the physics. And it's something I have to tune fairly often. So I'd like to just avoid that altogether if possible. It basically gives you something that is stable, that is practically stable for the actual implementation. It's not just theoretically stable. And while it doesn't completely rule out blow up due to something like non-physical solutions, it generally results in methods which are both high order accurate and stable out of the box. So here's an example. These are 4 different research groups, one in Saudi Arabia. These 2 down here are in Germany. These are some from our groups collaborating with someone at Virginia Tech. And all of these are basically run with exactly the same method. These are just standard, out-of-the-box, first-time implementation, entropy-stable methods where all we do is implement the method as is, run it, and we can deal with stuff like these nice turbulent-ish flows here, these shocks right here. Down here, you have some examples of turbulent-like behavior for magnetohydrodynamics. And so you have stable, reliable, high-order simulations without actually having to add any of these weird heuristic parameters. So I think for this reason, these methods have really been gaining popularity, and I mean that not just inside the academic circles, but at national labs, and even some industry partners are starting to actually look at this more. This is a list of results for in Google Scholar for basically entropy-stable methods and methods that I would consider kind of sisters to entropy-stable methods. So entropy-stable methods have been around for ages, from way before the 1990s, but they mostly were designed for first and second order schemes back then. That was pretty much the industry standard, and they worked fine. But they didn't add quite as much. What we found was that around 2010 was when folks figured out how to create entropy-stable methods that were also high-order accurate. And suddenly, you have this amazing symbiosis where you have this theoretical property that improves robustness. You have a class of supposedly revolutionary numerical methods that really have robustness issues. And when you join them together, you can see that the interest in these methods suddenly takes off. So let me give you a quick outline of the rest of the talk. I'm going to give you just, I hope, the briefest of intros to what entropy stable methods actually look like from a numerical methods perspective. I'm going to talk about this library, Trixie.jl, that I've been fortunate enough to be a part of. It's written in the Julia language, so I'll also talk about some of our experiences trying to bring Julia to scale and also to optimize, to bring HPC optimizations inside there. And then I'll talk about some of the details that were necessary to actually get this all to work. So I should note, my focus and my role in this library is primarily on theory and method development. So I work in the HPC adjacent areas, but the HPC results would not have been possible basically without the leadership of these two folks who have been part of the Julia of the Trixie team from day one, Hendrik Renoke and Michael Schlott-Kehle-Kemper. And in particular, they're the ones responsible for most of the impressive MPI results I'll show at the end. Okay, so hopefully this will be the briefest of introductions to what exactly these methods are doing. Here is the mathematical slide. I'm going to use a nodal discontinuous Galerkin method, collocation DG method, and if you're not familiar with any of these words, don't worry too much about it. We'll talk about a simpler matrix formulation next, but I want to at least give some background as to what we're doing. If you have something like a nonlinear conservation law, this is just a 1D example to make it simpler to show, then we do something that's pretty much akin to a standard finite element method. I multiply this by some basis function, I integrate by parts, and that gives me a residual, a weak formulation. I introduce, in particular, a numerical flux. This is a boundary integral where I couple together neighboring elements that are now discontinuous from each other using something like a fancy average. So this numerical flux is really the secret sauce of both finite volume and finite and discontinuous Galerkin methods. But we're just going to use it here as something that's given to us. I'm going to integrate by parts one more time to basically put myself in a slightly easier to look at formulation. And what I'm going to note is that this is using a very specific set of points to represent my solution. These are Gauss-Lobato points, which are essentially just some points which are really good for both polynomial interpolation and quadrature. Okay, so none of this is really important for the actual implementation. So let me boil this down to a much simpler slide. I have an equation up here, and if I were to squint, then I can imagine that this ODE down here, which is an ordinary differential equation on each individual element, kind of looks like this equation up here. I have a mass matrix. You can think of this as basically scaling by some grid size, which is varying between each node. I have something like a differentiation matrix. This is kind of like finite differences. It'll behave very similar in our setting. And I have some term that's basically going to couple elements together and also impose boundary conditions. We're going to try to explain how to turn this into an entropy stable method algebraically. So the main idea is actually pretty straightforward, and I apologize for throwing so much math in the very last talk of a very long day for y'all, but I hope this is an accessible enough idea to where you find a little bit of this as interesting as I do. I'm going to take this matrix vector product. This is basically trying to approximate a flux derivative in some form. I have some function. I want to differentiate it. That's numerical analysis 101. It's a matrix vector product, so I can just rewrite this as a summation for each individual entry. But if we know a little bit about this matrix, it's a difference matrix. It should differentiate. It should differentiate constants, and constants when differentiated are 0. So what that implies is actually my matrix has 0 row sums. I can add and subtract 0 and multiply by 1 in a kind of clever way and basically get that this matrix vector product, if this is a differentiation matrix, looks exactly like this summation over here. And this term over here, that's an average. That's just a very straightforward average of this nonlinear flux containing all of our physics at 2 individual grid points in an element. So this is a symmetric flux. You can think of it as a central or non-dissipative flux if you're familiar with finite volumes or finite differences. And the first thing that folks asked when they saw this is, what if we swap this for basically something else that looked like it? What if it's another average that's symmetric but has different properties? Maybe it's nonlinear. And it turns out that if you were to use something called an entropy conservative flux, then you end up getting some pretty nice properties out of it. So this is the main step. We take this matrix vector product, we rewrite it in this form that exposes the flux, we replace that flux with this additional flux, and there are some properties up here that don't really matter. They basically give you the theoretical stability that we're looking for. So we make this approximation, and just for convenience, I'm going to introduce a little bit of strange notation. This is a kind of cumbersome summation notation. I'm going to rewrite this as maybe a little more cumbersome, the Hadamard product between my differentiation matrix and a flux matrix that I'm basically forming on the fly, where it's just all the entries are individual flux evaluations containing the interactions between fluxes at different points. So this is just the point-wise product between two matrices, entry-wise. So it's what we hoped that matrix multiplication would be back when we were learning this. So I'm going to introduce this just because it'll be easier to manipulate later, but this is the main idea. Replace this flux with this one, and you magically get some nice properties. So what's the cost? Well, these fluxes, they exist. There are formulas for them. They are relatively complex and fairly expensive. This is an example of the compressible Euler equations and the corresponding entropy conservative flux that was derived back in 2013 for them. If you're familiar with the Euler equations, then you can see that this is mass, this is momentum, this is energy. But if you're not, don't worry too much about it. You essentially have the product of different averages. But the weird thing is, you have weird averages. You have this thing here. I don't know if you can see my pointer, but this logarithmic average is really non-standard. Turns out to actually show up in some weird thermodynamic cases, but you take the difference between two things in the numerator and the difference between their logarithms in the denominator. It looks strange. You have a bunch of odd variables. It's not entirely clear how to derive this without actually going through a fairly tedious derivation and verifying that it satisfies the theoretical properties we want. It's also relatively expensive, and we'll go a lot into this later. So we can use this, but there's a cost. And our focus in the HPC part is going to be to try to reduce this cost as much as possible. Okay, so to summarize, I have basically a standard DG, or kind of multi-domain finite difference type formulation. This is a system of ODEs on each individual element, and I'm just going to take this one single term and replace it by this. That's all. I modify only the local part. This should, of course, be fairly parallelizable. And we get this nice property that we can show something that's akin to the energy of this system actually is going to decrease in time. So we have the stability property. What that is isn't particularly important. It basically makes it so that our simulations are robust. Okay, so for the rest of the talk, I'm going to try and focus a little bit on what we did to try and optimize this within this Trixie.jl library. And I'm going to start by just describing a little bit of what this library does and why I'm interested in it. There are 5 principal developers. This was started in about 2021. I joined as the last principal developer exactly in 2021. And it has been surprisingly active, given that it was basically just an experiment by most of the principal developers in figuring out what Julia does. If you're not familiar with Julia, it is a programming language that claims to be as fast as C and C++, but have the expressibility of Python. And we wanted to test if that was true. So since then, we've had about 18, well, we have 18 current active contributors, several of whom are outside of our immediate circles, basically just people who found this code and are now contributing to it. We've had about 40 papers written with this since 2021, and there are a couple of folks downstream who are using this for actually Air Force simulations of hypersonic flows. So our focus is on making sure this code is extensible, reproducible, and highly performant. And if you're curious about why there's a picture of a witch, that turns out to be the reason why it's called Trixie. It's apparently a kid's cartoon in Germany, so they just made that their logo. Okay, here's some examples of pictures that you can get from this code. This is a Mach 3 flow over a step. Basically, think of it as a supersonic flow in something that looks kind of like a wind tunnel. And the important part that I want to point out is you have a bunch of discontinuities. So you have these shocks in the solution. You have these weird kind of wavy features up here. It's a reasonably complicated flow, but also overlaid is the mesh. So our mesh is actually going to be an adaptive mesh, where you can see that we have basically a collection of quad tree meshes that are locally refined basically to capture this shock solution with as few elements and degrees of freedom as possible. We have some fairly nice behavior here, but we can also do something a little bit more complicated. And you can do kind of the same type of simulation, but you can see it move dynamically. And this is flow over a wavy surface, where you have these beautiful little pictures of shocks that kind of come off each of these wavy bumps. And you can see the mesh get modified and adapted and change in time. We have a little bit of a shock indicator here to add some numerical diffusion. But by and large, the reason why this works and is robust is because of these entropy stable methods. We have also a simulation of flooding, which is generated by Andrew Winters, one of the developers. And this is actually Seaside, Oregon, where we actually tried to mesh this town and see what happens when we have a wave wash over it and basically flood this town and damage property. So These are useful in simulations of things like storm surge, and there we go. So you can see an example of the mesh here and the actual LiDAR image that we used to generate this. All the credit for this, by the way, when I say we, I mean the developer team. All the credit for this goes to Andrew Winters, who is one of the developers who had pioneered this work. We have some examples of actually adapting and extending this code. We have a bunch of pull requests that are constantly being reviewed and integrated. We try and make sure that other people can actually access this. But today I want to talk a little bit about the performance part of it. So I'm going to talk a little bit about Julia, just in case there are folks who are not familiar with the Julia language. As I mentioned before, this claims to have Python-like features and interactivity, but also C and C++ and Fortran level performance. So we wanted to put that to the test when designing Trixie.jl, while making sure that our code still remained extensible. So we didn't want to just throw in vectorization intrinsics everywhere, tie ourselves to one piece of hardware or one type of architecture. We want to make sure this can basically still be used on pretty much anybody's laptop, even ranging from an individual computer to a large cluster. And to do that, we're going to basically use a lot of Julia's features and also this nice aspect of Julia called multiple dispatch, which allows us to basically make non-invasive specializations, which improve extensibility. We also are going to take advantage of the fact that there's a very, very nice package manager for this. I know with HPC, a lot of us have faced massive headaches just installing packages, installing the dependencies for any particular HPC system. Julia has a package manager that not only installs native Julia packages really easily, but it also installs C and Fortran wrapper libraries. They call them JLL libraries in exactly the same fashion. So I can basically install something like mpi.jl, a wrapper around MPI, a wrapper around this pforest library, which is our mesh management library, with one single line. And it automatically works no matter what computer I'm on, no matter what architecture I'm working with. We're also going to use a bunch of the open source packages that have been developed by the Julia community to work on multi-threading, SIMD, and also temporal adaptivity for the simulation of all of our systems. Okay, with the remainder of the time I have, I'm just going to try and go a little bit into the steps that were necessary to make things efficient in Trixie.jl. And this will talk a little bit about low-level optimizations, a lot about the serial performance that we tried to squeeze out of it, and then I'll briefly touch on scaling and GPUs at the very end. So I want to figure out what the computational cost of these methods is. As I mentioned before, these fluxes that we end up having to evaluate a ton of times every single step of this simulation, these are going to by far be the computational bottleneck for these methods. So what we're going to do is try and make sure that we can minimize the number of fluxes that we have, that we can optimize the actual flux evaluations, and we'll basically show you some tricks that we found convenient in Julia for making this a little bit easier. We're going to focus on the 2D and 3D compressible Euler equations as a model problem, just because they have a fairly expensive flux. Okay, so the first step that we're going to do is we're going to take our numerical formulation and squeeze as much structure out of it as we can. We're working primarily on forests of quad trees and octrees, and these are basically squares and cubes. Squares and cubes tend to have a very nice line-by-line tensor product structure, and in this case, it's no different. It turns out that these flux evaluations that are buried in here can be decomposed so that they really only have to happen between sets of nodes in a line in each individual dimension. So already, this decreases the number of flux evaluations that we need to have on an element by a really significant factor. We can also do an additional trick where along each line, we can cut the number of flux evaluations we have to do in half by using some facts that we can, by using some numerical reformulations. We can basically take this Hadamard product. This is on-the-fly evaluations of these fluxes for every single non-zero entry of this matrix Q. We can basically replace this with a skew-symmetric matrix and use the fact that this flux matrix is symmetric. We know that this is just a skew-symmetric and symmetric matrix point-wise multiplied together, so we don't actually have to compute all of these fluxes. We can just compute basically the upper half of this skew-symmetric matrix and skip half of our flux evaluations. This is the numerical part. This is what anyone can do on any implementation. The more Julia-specific part was really trying to figure out how to squeeze serial performance out of this. And squeezing serial performance out of this really did help a bunch, especially when we compared our performance against another reference Fortran code. So getting a little bit more low level, we know that we have these flux evaluations, and if we profile them carefully, we can find that this logarithmic mean tends to be the dominant cost in these evaluations. This, you can see, divides by 0 if this UL, this U left and U right state are the same. So we have to avoid this by basically using this algorithm over here on the right. This is given by Ismail and Rowe back in 2009, and it basically does something like a Taylor expansion when UL is close to UR. So we implemented this at first, and this is the optimized version that we implement in our code. And it's a little bit hard to see, but the main difference is that here we have 2 divisions. And this is a really, really small difference, but ends up making a big difference in terms of runtime. We have basically 2 divisions here where we compute a ratio once and a ratio again. We can mathematically reformulate this so that we only have 1 division. And this ends up making a big difference because divisions are more expensive than multiplications, but also we're going to trade divisions for multiplications and additions, and those can be fused together using a little bit of Julia magic later on in order to improve our performance. We can do the same thing but for basically 1 over the log mean, which actually shows them our fluxes, but I'm not going to mention that. I'm going to talk a little bit about how Julia is able to give us a glimpse into what the compiler is actually doing as well. So we optimized the Julia code that we had. We compared against a very similar optimized Fortran library, and we noticed that it was significantly faster. It turned out that if we use Godbolt and use Julia's introspection utilities, that there is a very significant difference in the compiled instructions that both codes end up giving us. So when we were looking at Julia, it turned out that we weren't getting these fuse multiply adds, where you can do a multiply and addition all in one single instruction set, and our Fortran code was getting them. So to figure out why exactly this was the case, we have to go back to the fact that Julia, you can think of it as a language that's essentially a compiler that is turned into an entire language. So Julia takes code that looks like Python code, and before it runs it, it actually will compile it into something more low level, like either like an intermediate representation, which is then compiled into LLVM type instructions. And every single step of the way, you can analyze what exactly Julia is doing. It's not a very good compiler all the time. And what happens is that you can end up with fused multiply additions, or something like A times B plus C. And a good compiler would recognize this can be turned into a fused multiply add. Julia needs a little bit of additional hinting to kind of tell it that this can be turned into this specific instruction set. So there's this nice little package called this moladd macro, which will basically just decorate outside of a function. And what this does is it tries to auto-detect all of the operations that can be turned into fused multiply adds. And then you can see in this case, when we analyze what Julia is actually producing, you get these nice fused multiply adds. And just by adding basically these 8 lines of code, 8 characters, we already get 13% speed up against our reference. Adding an inline boosts things a little bit more. And along with the reformulations that I mentioned in the last step, we actually get a nice 35% speed up over the already fairly fast reference implementation that we started with. OK, so this doesn't seem that exciting. It's serial performance improvements. It's something that everyone does, and it's been known for quite a while. The thing that was nice was being able to use Julia's introspection tools to figure out how this is done. And we'll show you exactly how it behaves in terms of performance in a second. Julia also specializes on the mesh type. It basically tries to take advantage of as much information as we have. You can see that we have 3 different types of meshes here that are mainly supported. There's something like a Cartesian domain, which is a tree mesh, basically a quad tree. You have a structured mesh, which is what we call essentially a mapped Cartesian domain. And then you have a fully unstructured curved forest of quad and oct trees, which is this p-forest mesh over here. And these are increasing in complexity and also increasing in terms of the computational cost. So we're going to specialize in terms of these based on the operations that we can eliminate completely for these simpler meshes. So I'm going to skip this for the sake of time, but essentially what we get at the end is a couple of performance index plots like the following. So this performance index is the total runtime of a full simulation divided by, a single step in a full simulation divided by the number of right-hand side evaluations divided by the number of degrees of freedom. So you can think of this as just an index where the lower is better. It means either you can run a larger simulation for the same amount of time, or you can decrease the amount of time that you are spending running a simulation. So we're comparing against this red line here, which is Fluxo. This is a optimized Fortran library, and the thing that really surprised us was we have a much more, I think, extensible and maintainable code in Julia, and it actually beats Fluxo pretty handily for all the polynomial degrees we tried, from moderately high order, degree 3, to very high order, degree 15. We do better in all these cases, and I think this is a relatively fair comparison. Fluxo is actually doing a little bit more work than we are to try and optimize their code. They're cutting actually certain computations in half. We have to do twice as many variable transformations because they're pre-computing some variables, and this is a rather invasive operation. So they're doing more than we are, and at the same time, we still see that all of our meshes, no matter how complex, end up getting a slightly better performance index. And you can see there's a nice drop, especially at higher orders, in terms of the performance index. If you use this blue circle, this is the tree mesh, our Cartesian mesh, where we've tried to squeeze out as much performance as possible by taking advantage of the structure of the mesh and multiple dispatch. Okay, so with the time I have remaining, I'm just going to briefly talk about how we tried to introduce vectorization into our code in a maintainable and extensible way, and then I'll briefly talk about scaling. So we basically use an auto vectorizer, and this isn't that exciting, but what's interesting about it is that this auto vectorizer is fairly robust if the code around it is set up properly. So this is actually an example that I sometimes show to my, my undergraduate senior class, where I say this is just matrix multiplication. Simple, C is equal to A times B. And all I do is write it in the naive, non-block, non-cache block, non-recursive version. And I throw this macro in front of it. Think of it like just a transformation. This will take this code and modify it and aggressively apply loop restructuring, insert intermediate representations. It will basically transform this and try and squeeze as much performance out of it as you can. It gives me a 50 times speed up just by adding these 6 characters. And this is a simple example, but we're going to see that we get a similar significant improvement in performance if we use vectorization, this auto vectorizer, in Trixie. Now, this sounds simple. What I'm hiding is that there is quite a lot of work in making sure that this vectorization actually kicks in. If you have a code that is a little bit more complex than this, if your memory layout isn't structured entirely correctly, then basically this macro, this code transformation will just do nothing. It will leave it alone and you'll get the same performance as before. So we had to basically transpose some arrays. We had to make sure that the memory layout was appropriate for vectorization. We had to remove intermediate function calls. The code that we ended up producing is, I think, a little bit less extensible and maintainable because we had to special case a lot of it. But if you're really interested in the absolute highest performance, then that's, I think, what you need to do at the moment in Julia. And we managed to, I think, to get fairly consistent vectorization, 98% vectorization ratio for the most part. And here's an example of the actual improvement in runtime. This is the performance index for our previously optimized serial code in both 2D and in 3D for a couple different mesh types. And when you apply vectorization, when you apply this auto vectorizer, after doing all the work necessary to restructure the code so that it's amenable to vectorization, you end up getting this incredibly flat curve. That's a good thing. Previously, what we saw is that as we increased the polynomial degree, as we went to higher and higher orders, we ended up getting an increasing performance index. So things got less and less efficient per degree of freedom. With vectorization, you basically see no change as we go to higher order at all in 2D, and barely any change in the performance as we increase orders in 3D. Okay, I'm going to end off on just to mention that we have done scaling studies, but since I wasn't as closely involved with these, I'm just going to give the highlights. So first, if you want to parallelize, we now have vectorization. We have an optimized serial code. We're also going to throw in multi-threading, and this ends up actually being fairly trivial because we have a an explicit time-stepping solver. We can do what the folks in the energy community have been doing for finite differences for ages and just evaluate this in a matrix-free fashion. We basically had to use a fancy package to avoid a lot of the overhead that's in the native Julia thread scheduler, but that's a detail that we don't have to go into. For MPI, there was a lot more work that had to go into actually getting this scaling plot. And you can see that we can go up to about 60,000 ranks and still get reasonable scaling performance. It's a little bit of the superlinear behavior over here, which we're conjecturing is due to cache effects, but we're not really sure. This took a lot of work to actually set up. There were a huge number of memory issues. The fact that Julia is, is fairly memory hungry, and when you have 60,000 ranks, each with only a small amount of memory, we had to do a couple of things differently in order to make this work. We also are only including the actual computation time here. There's a lot of pre-compilation time, a lot of package loading time that we had to ignore. So this is definitely not ready, I think, for deployment yet. But at least when we're just looking at the computation, we do get the scalability that we expect. We do get the low-level code performance that Julia promises. We're working on GPU stuff right now, but since I'm running out of time, I'm going to go ahead and just mention that it shows a similar behavior where this blue is basically our entropy stable DG performance index, and it remains relatively flat up until moderate orders of approximation. So we basically are getting similar performance to our vectorization, where we can increase orders, we can add more complexity to this code without actually paying any computational cost. So currently we're working on this and trying to use something for portability, but I'm happy to, for now, just conclude by saying we've had a good experience with Julia. We have been applying mostly traditional HPC serial optimization techniques, but they've been much more pleasant and I think much more extensible and portable using the Julia language. You do have to know quite a lot about Julia's internals, which is a little bit tricky, but once you get there, I've been able to get code that was as fast as C and Fortran with significantly less effort while maintaining extensibility. So with that, I'd like to thank the organizers for inviting me. Thank you all for sticking around for this last talk. And I welcome any questions, or I think we might have an announcement from David. Thank you all.
Thank you, Jesse. Before we take questions, we do have, oh, never mind. We'll take questions first.
So a few years ago, Gregor Gassner sort of made a little splash by saying that entropy stable wasn't linearly stable. It only has this nonlinear stability property. Can you comment on sort of its usefulness, given that it's actually not linearly stable?
Yeah, so this is something that we actually have made some strides towards fixing. And I didn't include this because it's not optimized, it's not kind of part of the HPC story that we've been working on, but there are other ways to get the same property. So we did flux differencing, this kind of nice way of inserting entropy conservative fluxes to get this property, but we've been able to achieve it through some other approaches, some weird limiting that we designed. We've actually managed to recently get it through a very, very carefully designed artificial viscosity, and in these cases, you get the same overall stability property while also retaining linear stability. So we're pretty excited about this. The paper we just put out the preprint, so it's pretty fresh. We're hoping to integrate this into Trixie and scale things. And the nice thing about it is because this skips some of the weird algebraic reformulation steps, we think we can actually get an even more performant implementation. But there's nothing too new about this because it's then going to be using old finite element tools, kind of the way that they were designed. Yeah, thanks.
Any other questions? Oh, yeah.
Okay, so I have a question about the entropy stable method. What's the advantage over energy stable method, and is it better to be used in CFD over like other applications? Thank you.
Yeah, thanks for the question. So an entropy stable method is, I think of it as a generalization of an entropy stable method I think of as a generalization of an energy stable method. A lot of the times I'm looking at a complex system, let's say compressible Euler, magnetohydrodynamics, even multi-species or reactive flows, all of these are pretty complex, but they all obey an entropy inequality. They don't necessarily give you an energy inequality. So if I construct something that's energy stable, then I think I essentially get something that, as Jeremy was mentioning, is probably linearly stable. So if I linearize the system, then I can get stability for this. But this is a stronger property in the sense that this is a nonlinear stability. I can evolve this equation kind of infinitely far ahead in time, and as long as I don't get non-physical solution variables like negative density, negative pressure, or temperature, then this can run indefinitely. And that's a much stronger statement than just energy stability. In practice, I think it depends a little bit on, well, what you're really simulating. A lot of the energy stable methods will perform equally well for kind of smooth, nice flows. But when you get to something under-resolved with shocks, with turbulence, then I find these entropy stable methods to often be a little bit more robust. Thank you.
All right, thank you very much, Jesse. Appreciate it.
Thank you.